Okay, let's continue the discussion. In 2.36, we proved that xn converges to x if and only if the lim sup is equal to the lim inf is equal to x. Okay, so the convergence can be characterized by the definition of lim sup and lim inf. This is on 2.36. And what happens if the total sequence does not converge, but it contains a convergent subsequence? Okay, so that's the theorem 2.37. Okay, so let xn be a sequence of real numbers. Then the lim sup is the largest value to which some subsequence of xn converges. Okay, and similarly, the lim inf of xn is the smallest value to which some subsequence of xn converges. Okay, and well, the statement gave a different characterization, namely, if we have a subsequence xnk converges to x as k approaches infinity, then this limit x is greater than or equal to the lim inf of xn and less than or equal to the lim sup of xn. So the lim inf, lim sup will always squeeze the limit of the subsequence. All right, and this definition, actually, this result, namely, it is not equivalent to the statement here. Remember that in the theorem 2.35, it says if you have a finite lim inf and lim sup, there always exists a subsequence converge to lim sup and another sequence converge to lim inf. Okay, so you can always do that. I mean here it's not necessary to have the finite number. It can be infinite, but anyway, you can always find the subsequence converge to the lim sup and the lim inf, and in any subsequence, convergent subsequence with the limit x will be bounded by them. So combine these two, this namely statement plus a theorem 2.35 together is equivalent to the statement 2.37. Okay, so it's a largest possible value for the subsequence of xn to converge, or the smallest possible value to which the subsequence of xn converge. Here, just say they are bound, but this part, they don't claim the existence of a subsequence. And 2.35 claim you can find subsequence converge to the lim-inf and converge to lim-sup. Okay, so it's not exactly equivalent to it. You have to use the theorem 2.35. Okay, so let's try to prove this. Let's try to prove 2.37. Okay, so assume that a subsequence xnk converges to x as k approaches infinity. Okay, then fix n, capital N, in the natural numbers, and we choose capital K, so that K greater than capital K, then n sub k is greater than or equal to capital N. Okay? Okay, so let's check. Xnk, under this condition, xnk is any is an arbitrary element in the tail. Okay, arbitrary element in the tail. And remember that nk is greater than n. So of course it's less than the supremum of x, well, let's see, xj, j is greater than or equal to n. Okay, it's less than the supremum, xjj is greater than or equal to n. And of course it's greater than or equal to the infimum, xj, j is greater than or equal to n. Right, you choose supremum, you choose infimum, definitely it's correct. And because when little k is greater than or equal to capital K, nk is greater than capital N. So we have this inequality for all little k greater than or equal to capital K. Little k greater than or equal to capital K. Okay, so basically you just pick up the element, the proper sufficiently large subindex from the subsequence. Okay, and be careful. In this step, you cannot let n approach infinity. You cannot let n approach infinity, because remember that when n becomes bigger and bigger, eventually this capital N will be greater than n sub k. So that's not allowed, because when capital N is greater than n sub k, this inequality will not hold. Okay? So the right order is the following. Here, we let little k approach infinity. This is fixed. N is fixed. N is fixed. This works for all little k greater than capital K. So this one is free. This index k is free. So you let k approach infinity. When k is bigger and bigger, this condition is always satisfied. This inequality is always satisfied. Let k approach infinity, x and k will approach or will converge to x. Okay, then this is a fixed number. Be careful. This is a fixed number. This is a fixed number. Then by the comparison of the limit, we have x between the supremum j greater than or equal to n, xj. Here is the infimum j greater than or equal to capital N, xj. Okay, so this process, we change the middle term first. The middle term is free. You can let it as big as possible. N is not free, so that's why we say fix n. Okay, so after you get this, the middle term is fixed, and this term depend on capital N for whatever, for arbitrary, for any. For any natural number n, you have this property. And then, again, apply the comparison of limit letting n approach infinity. When we let n approach infinity, this one has a limit. It's a decreasing sequence. So we have, here is a decreasing, here is increasing, then this becomes a lim inf n approach infinity xn lim sup xn n approach infinity. Okay, so this is what we want. This is what we want. Okay, so this proof is not difficult. It's just application of two comparisons of limits. The comparisons of limits. But for those two applications of a comparison of a limit, you have to be careful about the order. You can only handle the middle term first, because the middle term is free with respect to capital N. After you get a fixed number, you let capital N approach infinity. Okay, so that's the point I want to emphasize. I want to emphasize. Okay, so you still from here you can see that this result is not equivalent to the original one. It just say the limit of the subsequence will be bounded by those two numbers. It does not say those two numbers can be achieved, can be reached. That part is done by the theorem 2.35. You combine 2.35 with our proof, it proves the real result of 37. Lim sup is the largest value and the lim inf is the smallest value. Okay, that's the case. Okay, so the simple remark is that if xn is any sequence of real numbers, then the lim inf of xn n approaching infinity is always less than or equal to the lim sup of xn n approaching infinity. Actually, this is a simple corollary of the previous result. You see here, lim inf is less than or equal to lim sup through the bridge x. Okay, so it's just a simple corollary of the previous remark. Lim sup is always less than it. And of course, you can start from the comparison theorem and try to get the theorem. So you're going to directly get this one is less than or equal to this one. Inf j greater than or equal to n is less than or equal to sup j is greater than or equal to n. Okay, so you start from here. You can also reach the theorem. Okay, so anyway, we consider it as a corollary of the first of the previous theorem. It's a corollary of a 2.37. And another remark another remark says a real sequence xn is bounded above if and only if the lim sup of xn and approaching infinity is a finite number. It is a finite number. And okay, bounded above if and only if the lim sup is a finite number. Is bounded below if and only if the lim inf is greater than negative infinity. I'm sorry, not 8, infinity. Yeah, this is the right direction. It's greater than negative infinity. That's lim, if it's bounded below. Okay, so how do we understand it? How do we understand it? If we will just do one. If xn is bounded above there is in capital M such that xn is less than or equal to capital M for all n in the natural numbers. And then the supremum of j greater than or equal to n xj is also less than or equal to m. Even you take the supremum, it's also less than or equal to m. And then you take the limit approaching infinity, xn is going to be less than or equal to m. So it's a bounded above. It is a finite number, non-negative, non-infinity. Okay? So this is one direction. The other direction, if the lim sup of xn, and approaching infinity is equal to some m, is equal to certain m, then it means for any epsilon greater than 0, there exists capital N in a set of natural numbers such that for all n greater than or equal to capital N, the supremum j greater than or equal to n, what is it, xj, it is less than, it is minus the limit is, we call it m, okay, is between epsilon, is bounded by epsilon, right? That's a limit, the definition of the limit. And to write it, it is a supremum xj, j greater than or equal to n, minus m is bounded by epsilon and negative epsilon. Okay? Epsilon and negative epsilon. And you move the m to the right side, you will get the supremum of xj is less than m plus epsilon j greater than or equal to n. Right? It's one direction, it's not equivalent. We just need the right part. It's bounded above. Okay, and then choose capital N prime be ops value of x1 plus ops value of x2 plus blah 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 plus ops value of x, here is n, then let's choose n minus 1 and plus m plus epsilon. We choose a bigger number. We just add So here, this supermom controls the tail. So you still have finite element less with the index less than n. So just add, put the ups value, add all of them. Then x n x j will be less than or equal to m prime for all j in natural numbers. Okay? So if j is smaller, then xj is less than its ups value, is of course. When j is bigger than n, it is less than m plus epsilon by this condition. So either way, it's going to be bounded above. Right? You see how I go through it? So you have bounded above from the finiteness of the lim sup. You can also get bounded below from the lim inf result. So you are going to go through it by yourself. It is not difficult. It's very short. It's very straightforward. And actually, if you use the lim inf, you're going to use the left inequality. All right? Okay. So this is the remark 2.39. And the last stuff is a comparison theorem for the lim inf and the lim sup. It says if xn less than or equal to yn for n large, sufficiently large n, then the lim sup of xn n approaching infinity is less than or equal to the lim sup of yn n approaching infinity. Remember, if we have the convergent sequence, then the limit of xn is less than or equal to the limit of yn, just one statement. But here, because we only assume xn and yn, we don't know if they are convergent or not. So we can only put the lim sup for xn and lim sup for yn here. And we have lim inf xn and lim inf yn. Okay, so you can put it here. And the proof is again application of a comparison theorem, the comparison of the limit. Why? Because the lim sup lim inf are defined by the supermom of xj and the supermom of yj. Because xn is less than or equal to yn for sufficiently large n, for large n, the supermom of xj, j greater than or equal to n, is less than or equal to the supermom of yj, j greater than or equal to n. That's a clear stuff. And then you kind of construct two new sequences, and they are decreasing. Then you apply the comparison test for the sequence. This is convergent sequence, or even convergent to negative infinity. It's okay. It's a convergent sequence. So then by the comparison theorem, of the limit, we let n approach infinity, we will have the lim sup xn approaching infinity is less than or equal to the lim sup yn approaching infinity. Right? So again, the lim sup lim inf, they are defined for all sequences, but still the definition of lim sup lim inf depend on the limit of certain derived sequences. Okay, so whenever you can apply the sequence theorem to the regular convergent sequence, you possibly can apply the similar theorem to the lim sup and the lim inf. Okay, so this is a section 2.5. Now let's see the exercise. Exercise is on page 55. Well, you can try the problem 2. Problem 3. And problem 4. And problem 5A. Let's just do 5A. Problem 5A and problem 6. Well, if you have time, you can try them. Okay? So this is the section 2.5. 2.5 actually contains more interesting exercise. If you want, you can try more. They just help you to understand the process of the proof about the limit or lim_sup and the lim_inf. All right? Okay, so we finished the chapter 2. Now let's move to the chapter 3. We talk about the continuity on R. Okay, so first section, 3.1, two-sided limits. Two-sided limits. First, let's define the limit of the function. Well, it's identical to the limit you learn in calculus, but still, let's reproduce them, and we will see some exercise. Okay, 3.1 definition. Let A be in R, a real number. Let I be an open interval. That contains A. And let F be a real function defined everywhere on I on this open interval except possibly at A. Maybe it is undefined at A, may or may not, okay? So it's possibly except at A. Then fx is said to converge to L as x approaches A if and only if for every epsilon greater than 0 there is a delta greater than 0. Okay, so here that's something we emphasize, which in general depends on all the conditions you have. You see here, before delta you have epsilon. You have this function f, where's the function? Function f. You have a point A. You have an interval I. So it depends on epsilon, f, I, and A. Okay? So in general, it depends on all the informations you mentioned at the beginning. When those information are fixed, you can find this delta. Okay? such that zero less than ops value of x minus a less than delta when the distance between x and a is sufficiently small implies fx minus L ops value less than epsilon. The image is arbitrarily close to the limit. Okay? The image will be arbitrarily close to the limit if the input x is sufficiently close to the a. And in this case, when this happens, in this case, we write the limit is L is equal to the limit fx x approaches a. Sorry, x approaches a. The limit fx as x approaching a. Okay. Well, we call L the limit of fx as x approaches a. Okay, let me write that again. The limit x approaches a fx. The limit of fx as x approaches a. Okay, the same thing, the same. This is one of the fundamental and the important definition in the calculus and analysis. So from here, we put our basis of the analysis on ground. It's not like the verbal definition of the limit. We always say fx can be arbitrarily close to L if x is sufficiently close to a. But that depends on the the word, sufficient, arbitrary. Those are very subtle words. And when you have epsilon and delta, they are quantitative. It's much fundamental, okay? Okay, so now let's prove that. The first example. Suppose, well, possibly I will skip it. Suppose that fx is equal to mx plus b. If you have a linear function where m and b are in R, then prove that fx x approaches a is equal to fa for all a in R. Well, you are going to prove it. Actually, even in the calculus, you learn how to prove it. It's not difficult at all. Okay. So I'm going to present the next one. The next one is much more important because this one, if you try to find the delta, you will see that the delta only depends on epsilon. It does not depend on the other stuffs. Of course, delta depends on f, but the delta does not depend on a. Okay, so it depends on function. It depends on epsilon, but it does not depend on a. It's we call it uniform. And the next one, 3.3 example, we will see this delta. It depends on epsilon, depends on f. It also depends on a. Okay, example. If fx is equal to x squared plus x minus 3. Okay, prove that fx converges to -1 as x approaches +1. Okay. Here, let me write. Delta does not depend on a. So this is later we will see this called a uniform limit, the limited continuity, the uniform continuity. Here, let's try to prove it. So prove given epsilon for all epsilon greater than 0. L, what is L? L is equal to -1. Okay, so basically we want analysis first. We check this fx minus L. We check fx minus L. fx, where's fx? Okay, here. X squared plus x minus 3 and minus L. Minus -1 is +1. So it's x squared plus x minus 2. In this one we can factor it. So factor it is x plus 2, x minus 1. Okay? Okay, now let's see. We are going to choose delta. Delta should be very, very small, right? We need the x sufficiently close to a. So delta is that represent as sufficient. So delta will be very small. So if this delta is between 0 and 1, if it's delta between 0 and 1, then we have the requirement x minus a less than delta. We have this requirement x minus a less than delta. X minus a less than delta, then what do we have? We have x minus 1 is less than delta, so its upper value will be less than 1, less than delta. Delta is less than 1, so x minus 1 is less than 1, upper value less than 1, so x minus 1 is less than 1, greater than -1. So add a 1 for 3 sides, so 0 less than x less than 2. So we do have a positive number. Okay, we want a positive number. So here you don't see the dependence of delta with the point 1. Actually, here by the proper selection, we make this right side positive. Okay, so we make this right side 0 so that x is always a positive number. Okay. Okay, now let's see. By the triangle inequality, upper value of x plus 2 is less than or equal to upper value of x and then plus upper value of 2. X is positive, x is equal to upper value of x. So upper value of x is between 0 and 2, so it's less than 2 plus 2 is equal to 4. So the coefficient, you consider this part, upper value less than equal to 4. Okay, so in order to have upper value of fx minus L, which is upper value of x plus 2, x minus 1. You check here, this one, yes, this one is delta. X minus 1 is less than delta. And this one, we just control it. It's x plus 2 upper value is less than 4. So it's less than 4 times delta. We assume x is very small. And if we require 4 delta less than epsilon, then it's solved, right? This delta is arbitrary. Any smaller number between 0 and between 0 and 1 will play the same role. Okay, any number will play the same. So here this delta is free. It's not it does not contain a lot of a special property. It's free. It's free to be arbitrarily small. Okay, so here we require 4 delta less than epsilon, so delta less than epsilon over 4. We require delta less than epsilon over 4. And this condition has assumption delta is between 0 and 1. Hence, for delta less than epsilon over 4 and delta less than 1, less than both of them, less than both of them. How do we get both of them? We choose delta to be the minimum less than or equal to the minimum of epsilon over 4 and 1. We choose this. If you are not so sure about the equal case, you put 1/2 here. Okay, anyway, we choose delta to be the minimum among them. It means we are going to keep those two conditions. When those two conditions satisfied, for x minus a ups value less than delta, for this one, not than, if, this is if, the word if, my bad. For x minus 1 ups value less than delta, then you will have x plus 2 ups value less than 4, and this one, it is less than 4 delta. You just go through this part and less than epsilon. 4 delta is less than epsilon. So for any epsilon, you can find a delta such that whenever x minus 1 ups value less than delta, fx minus L ups value is less than epsilon. So by the definition, of the limit fx x approaches 1 is equal to -1. Okay? Okay, so that's our stuff. Okay? So go through this process, you will see that in many proofs related to the polynomials, you will be able to factor the polynomial, the difference, into certain product. In that factorization, x minus 1 is always kept. You do not manipulate that term, because that term will be controlled by delta. What you need to control is the coefficient. You should have coefficient less than or equal to certain number. In other words, the coefficient should be bounded. So x plus 2 ups value should be bounded. Here we show it is bounded by 4. Okay? So once you get this boundedness, and in order to prove it is bounded, you possibly will pre-assume delta satisfies certain condition. Here we assume delta is between 0 and -1. Okay? It satisfies certain condition. And when this is bounded, you put this bounds 4 here and divide by 4, divided by the bounds, you get epsilon over the bounds, epsilon over 4. And this condition plus the pre-selected condition, you need to consider both conditions in order to get the ups value of the difference less than epsilon. But anyway, you will have finitely many such conditions. Then you just choose a minimum. Choose a minimum, that's okay. Okay? And then you just go through it formally like the definition. All right? So this is the proof of a 3.3 example. How do we show that the limit of a quadratic polynomial by the definition? Okay. Let's see. Here in the definition of the limit, we always say function f is defined everywhere in that open neighborhood I, except possibly at a. Except possibly at a. So which means we even don't care if function is defined or not at a. So the remark 3.4 make this even more clear. So let A be in R. Let I be an open interval that contains A. and let f and g be real functions defined everywhere on I except possibly at A. If fx is equal to gx for all x in I but not equal to A, and fx converges to L as x approaches A, then gx also has a limit as x approaches A, and the limit g of x approaches A is equal to the limit fx x approaches A. Okay, so this remark just say those two functions, they are equal to each other, possibly only except this A. One has a limit, the other one also has the same limit. So I can define the function at A with whatever value. Keep other points, the definition over other points. Just randomly change the value at this point A, but you do not change the limit at A. In other words, the limit is the characterization of the behavior function around the point, but not at the point. Around the point, we're going to talk about the environment, not talking about this specific point. Okay, so how do we prove it? Prove given epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus a ups value less than delta greater than 0. So this is important step. This is crucial. Okay, so whenever this happens, the fx minus L is less than epsilon. This, yes, yeah, this is the limit of f. So this is exactly the definition of fx has a limit L at A. For epsilon greater than 0 is a delta such that x minus a less than delta greater than 0, not equal to A. This implies x is not equal to A. Then fx minus L is less than delta and less than epsilon. And here, x minus a is greater than 0 implies x is not equal to A. Then x is not equal to A, fx is equal to gx. Okay, fx is equal to gx. So let's rewrite this sentence again. For every epsilon greater than 0, there exists a delta greater than 0 such that whenever x minus a less than delta greater than A, here f is g, so gx minus L is less than epsilon. What is this? This is exactly by the definition of the limit. The limit of gx, x approaches A, is also equal to L. Okay, so that's the proof. That's a proof. Okay, so the remark just gave us the idea how independence of the values of function f at that point A. So we don't care the value. It may or may not define. It may be defined with whatever value. Once you fix the environment, you know the behavior function around it, you will actually already determine the limit of function when x approaches it. Okay, so that's the case. Okay, so next we're going to study the example about this remark 3.4. and we will continue in a different video. Okay, thank you.